Welcome to The Explainer. I am so excited you're joining me today because, well, we're diving into something that literally affects almost every single shop, fabricator, and designer in North America. Okay, let's just get right into it. We are going to uncover this massive, costly secret that's basically been hiding in plain sight within the plastics and fabrication trade. It's a secret that sits quietly on almost every purchase order you write, and honestly, if you don't know what to look for, it's probably costing you time, money, and just a whole lot of unnecessary frustration on the shop floor. Today, we're cutting through all the confusion to reveal the true meaning behind gauges.
So let's start with just a rock-solid basic fact. If you pull out a standard tape measure right now, or, ask a machinist to do a quick conversion, 1/4 of an inch translates perfectly to 6.35 millimeters. It's a mathematical certainty, right? It's exactly what your CNC router expects when you program it, it's what your table saw is set to clear, and it's the exact precise dimension you'd use to cut a perfectly snug channel. In a perfect world, you'd totally expect the physical material to match the math.
But that brings us to a really fascinating dilemma. When is a 1/4 inch sheet absolutely not a 1/4 inch sheet? Well, the answer is almost always, at least when you're buying acrylic. Here is the bold truth, straight from the data. In the North American acrylic trade, the imperial measurements you rely on every single day, they are a complete illusion. You might confidently write 1/4 inch on your order form, but what actually shows up on the delivery truck is playing by an entirely different set of rules.
To really understand why this happens, we have to separate the nominal label from the actual measurement. You see, the imperial gauge names used by the trade, like calling something 1/8 of an inch or 1/4 of an inch, they're merely nominal labels. They are, for all intents and purposes, just conversational shorthand. Sure, they make it super easy to talk over the phone or quickly jot down a quote, but they are absolutely not actual physical measurements. And if you take that shorthand as literal millimeter reality, man, you are setting yourself up for failure before the very first cut is even made.
Just think about how stark the difference actually is when we dig into the raw numbers. Take a so-called 1/4 inch sheet of cast acrylic, for example. Physically, it is actually 5.5 millimeters. Now, if you order extruded acrylic instead, it's 6 millimeters. But the true imperial equivalent of a 1/4 inch is 6.35 millimeters. So it is literally never a true 6.35 millimeters. Or think about 1/2 inch material. It's 12 millimeters in cast, nowhere near the true 12.7. It's total chaos, really. You have the name of the product, the physical reality of cast, the physical reality of extruded, and absolutely none of them perfectly align with true imperial math. Let's look at how this fuzzy math translates into a very real, very painful problem on the shop floor. Between the true math and the cast reality, we're looking at a gap of 0.85 millimeters. Now, on paper, a sub-millimeter difference might seem tiny, right? Almost negligible. But in fabrication, oh man, 0.85 millimeters is a canyon. This is the exact amount of disastrous slop created when a shop programs their router to cut a true 6.35 millimeter channel for a sheet they firmly believe is a 1/4 inch, but they actually receive a 5.5 millimeter cast sheet. That sheet slides into the channel, and suddenly, boom, you have nearly a full millimeter of empty, useless space.
And that empty space? It leads directly to some serious downstream nightmares. This isn't just some abstract math problem for nerds. There are tangible, financial consequences to this gap. That 0.85 millimeters of slop means you're building sign faces that rattle every single time the wind blows. It means you're creating these ugly, uneven shadow lines along illuminated edges because the fit just isn't flush. Imagine a cabinet maker cutting a 6 millimeter dado for a cast acrylic sheet. They finish with a 1/2 millimeter of looseness on every single joint. The absolute worst part is that this error always surfaces late. It ruins joints, compromises your final product, and usually you only discover it after the parts are already cut and paid for. But here is where we get to turn all this insider knowledge to our advantage. Let's pivot away from those shop floor errors for a second and reveal a hidden superpower. Once you stop relying on the imperial illusion and start embracing exact metric gauges, you unlock the physics of stiffness. Truly understanding exactly how thick your material is in millimeters allows you to engineer your projects so much more efficiently. It totally changes how you buy, and more importantly, how you build.
Here is a wild fact. In acrylic, panel rigidity roughly scales with the cube of the thickness. Okay, so what does that actually mean for you? Well, if you step up from a 4.3 millimeter sheet, which the trade casually calls 3/16, to a 5.5 millimeter sheet, the so-called 1/4 inch, you are only using about 25% more physical material. That means your material cost only goes up by roughly 25%. But because of the physics of stiffness, that relatively small jump in thickness returns close to double the resistance to bowing. You're getting a nearly 100% increase in rigidity for a fraction of the cost. And you know what? You can only make strategic, money-saving design choices like this when you are working with the real millimeter data, not just the conversational shorthand.
Right, and while we're busting industry myths today, we absolutely have to talk about what I like to call the extruded illusion. In the trade, extruded acrylic is widely traded as the budget grade, the cheap option compared to cast acrylic. And honestly, the very thinnest 2mm end of the spectrum, that's somewhat true. But that truth stops very, very quickly. Because the price gap between a sheet of cast and a sheet of extruded is basically a flat $2.26 per 4x8 sheet.
Why does that flat rate matter? Because as the sheets get thicker and naturally more expensive, that flat $2 discount completely collapses as a percentage. Which leads us to this incredibly fascinating industry pricing secret. From 2mm all the way up to 25mm, acrylic is priced almost purely on raw millimeter volume. Seriously, take the square foot price and divide it by the millimeter thickness. Across the board, it costs between 78 and 85 cents per square foot for each millimeter of thickness. There are no magic deals hiding in the middle gauges. It's just straightforward, simple volume pricing.
Understanding that pricing structure leads us to one golden rule. The only way to truly save money is to specify the thinnest sheet that meets the stiffness requirement. Since there are no secret value gauges that are quietly priced better than their neighbors, the ultimate way to save your shop money is to leverage that stiffness data we talked about earlier. Figure out exactly how much rigidity your project needs to prevent bowing or sagging, and simply order the thinnest metric sheet that accomplishes that goal.
Okay, so how do we actually put all of this into practice? Well, here is the ultimate zero-cost resolution to fix this entire issue on your very next purchase order. It's just 3 simple steps. Step 1, specify millimeters on all your drawings and your POs. Step 2, treat the imperial names entirely as conversational shorthand and nothing more. Step 3, always confirm the true metric figure before machining anything that has to receive that sheet. It costs literally nothing to implement this workflow, but man, it will save you from ruined parts, wasted material, and all those downstream nightmares.
Which leaves us with this final thought for today's explainer. You now know the massive difference between the name of the gauge and the physical reality of the sheet. You understand the very real financial impact of that sub-millimeter gap, and you know how to leverage the physics of stiffness to your advantage. So the next time you order materials, are you going to trust the label, or are you going to demand the measurement? Start using the real math today and just watch how it transforms your precision and your bottom line. Thanks so much for joining me on The Explainer. Keep asking those tough questions, keep demanding the real measurements, and I'll catch you next time.